Welcome to the training for Mechanical Science Fundamentals, Actuators. The average time to complete this training is estimated to be 25 minutes. After you have completed this portion of training, you will be directed to the next training lesson in this series for further instructions. So far, we have examined many types of valves. To serve their purposes, most valves have to be operated, open, closed, or throttled. In this module, we will look at different types of actuators that are used to position valves. The type of actuator attached to a valve is determined by its application, location, and operating characteristics. Some valves are purely for isolation, while others are used to regulate or throttle flow and adjust flow as needed to maintain process parameters. We will look at actuators commonly in use here at LWO. These are the objectives for this course. The most common type of mechanical actuator, and the one you are probably the most familiar with, is the hand wheel. Hand wheels directly operate the valve disc by moving the stem. Typically, when the hand wheel is turned clockwise or to the right, the valve disc is moved towards a closed position. When the hand wheel is moved counterclockwise or to the left, the valve disc is moved toward the open position. These valves' opening and closing procedures are sometimes referred to as righty-tighty and lefty-loosey. The manual actuator or hand wheel has two primary shapes. The more common design is the wheel shape. The lever shape is designed for valves that be quick acting like the ball, butterfly, or plug valves. If installed properly, when the lever is lined up with the piping, the valve is open. When the hand wheel is perpendicular to the pipe, the valve is closed. The failure mode for a hand wheel is as is. They are used in areas that operators can normally access. To close a hand wheel valve, turn in the clockwise direction or to the right. To open a hand wheel, turn in the counterclockwise direction or to the left. Easy reminder, righty-tighty, lefty-loosey. For large and or heavy manually operated valves, the bonnet may be fitted with a manually operated gear head. A special wrench or hand wheel attached to the pinion shaft permits one person to operate the valve when two people might be needed without the gear advantage. Because of the small size of the pinion, it takes longer to open a valve with the gearbox. The gears use the mechanical leverage provided by the different size gears to move larger valves. Just like the other manually operated valves, the failure mode is as is. It is used in accessible areas, also righty-tighty. Because several turns of the pinion are necessary to produce one turn of the valve stem, the operating time of large valves can be exceptionally long. If the valve is inaccessible during normal operations due to being in the overhead, or is so big that a standard hand wheel will not provide sufficient leverage, a chain wheel actuator may be installed. Typically, this actuator is used when the valves are above reachable level and scaffolding or platforms are not available to operate the valve safely. When operating any manual valve, wear gloves, not like this guy. It is especially important when operating chain wheel actuators. The chains are sized to make it easily accessible and operable from normal levels. Just like other manually operated valves, the failure mode is as is used in accessible areas, and righty-tighty. Electric motors permit manual, semi-automatic, and fully automatic operation of the valve. Motors are used mostly for open-close functions, although they can be used to put the valve in a mid-position. Motor-operated valves, or MOVs, provide the high torque, reliability, and relative ease of control. This is a symbol for an MOV. The normal operation is via the electronic motor through gearing to the valve stem. A manual hand wheel is often provided to allow positioning of the valve if the power fails. To protect the operator during manual operation, motor-operated valves typically use a power disconnect switch or clutch. The disconnect or clutch prevents motor operation while the manual hand wheel is in use. The advantage of an electric motor-operated valve actuator is that the electric motor can be sized to provide the large amount of torque required to open large valves. It can also provide intermediate positioning of valves. For the electric motor actuator, failure mode is as is. It can be operated remotely, can be used to throttle valves, and can be used on large valves. If power is lost, it can be manually repositioned using a hand wheel if available. Solenoid actuators provide automatic, two-position, open or closed, valve control. This is a symbol for a solenoid actuator. Solenoids are only capable of either fully opening or fully closing a valve. That is, solenoids are either on, energized, or off, de-energized. Solenoid actuators use magnetic force to move the stem of a valve. We know that a piece of iron is attracted to a magnet. In a solenoid valve, a current-carrying coil produces a magnetic field and attracts an iron plunger that is attached to a valve stem. The plunger moves up against spring pressure into the magnetic center of the coil. As a plunger moves up into the coil, it moves the valve stem, which opens or closes the valve depending on the design. When the electrical power is removed from the coil de-energizes and the spring repositions the stem, which closes or opens the valve. The failure mode of a solenoid actuator depends on design. They can be designed to energize to open or energize to close. A solenoid actuator can be operated remotely. It cannot be used to throttle valves. The amount of torque is limited by the size of the solenoid, so solenoids are typically only used on smaller valves. Another disadvantage of solenoid actuators is that the indication provided is not an indication that the valve is open or closed, only that the solenoid is energized or de-energized. An auxiliary use of the solenoid valve is to start or stop airflow to an air-actuated valve to open or close the valve. Pneumatic diaphragm actuators provide automatic or semi-automatic valve operation to open, close, or throttle a valve. This is a symbol for a diaphragm actuator. A diaphragm, usually made of rubber and a metal plate, which stiffens and supports the diaphragm, is bolted to a dished metal head to form a pressure-tight compartment. An air supply is connected to the pressure-tight compartment. The valve stem is attached to the diaphragm so that any movement of the diaphragm produces valve stem and disc movement. Motion of the diaphragm is opposed by a spring or by pressure on the opposite side of the diaphragm. The pneumatic actuator can have air on top of the diaphragm, below the diaphragm, or both. Here we see an air added below the diaphragm so that when air pressure increases, it lifts the stem and in this case the disc off the seat. For an air on bottom actuator, air pressure is applied to the bottom of the diaphragm, which is connected to the valve stem. The force applied to the diaphragm causes the diaphragm to flex upward against spring tension as the air pressure increases. Since the diaphragm is connected to the valve stem moves upward as the diaphragm flexes. The magnitude of the applied air pressure determines how far the valve travels. This configuration can be set up to open or close the valve on upward movement based on whether the valve is normal seated or reverse seated. With air on the bottom, if it is reverse seated, then the valve will close on increasing air pressure. If the valve is normal seated, then the valve will open on increasing air pressure. In an air on top diaphragm, air pressure is applied to the top of the diaphragm, which is connected to the valve stem. The force applied to the diaphragm causes the diaphragm to flex downward against spring tension as the air pressure increases. Since the diaphragm is connected to the valve stem moves downward as the diaphragm flexes. The magnitude of the applied air pressure determines how far the valve travels. This configuration can be set up to open or close the valve on downward movement based on whether the valve is normal seated or reverse seated. With air on top, if it is a reverse seated valve, then the valve will open on increasing air pressure. If the valve is normal seated, then the valve will close on increasing air pressure. For a pneumatic diaphragm actuator, the failure mode depends on the arrangement. A forward-acting actuator opens its valve on increasing air pressure. A reverse-acting actuator closes its valve on increasing air pressure. Both forward-acting and reverse-acting actuators are opposed by a spring which returns the valve to its normal or shelf state position when the air pressure is removed. This actuator can be operated remotely and can be used to throttle valves. A single-acting actuator has air on one side of the diaphragm and a spring on the other. A double-acting actuator has air acting on both sides of the diaphragm. Single-acting is by far the most prevalent in LWO. The pneumatic piston actuator works on the same physical principle as a diaphragm actuator. The difference is that the valve stem is connected to a piston rather than a flexible diaphragm. An air pressure connection supplies air to the cylinder either above or below the piston. In a single-acting actuator, the other side of the piston is vented to atmospheric pressure. The differential pressure across the piston moves the piston in the cylinder. When all pressure is removed, an internal spring repositions the valve to its fail position. Just like the diaphragm actuator, the piston actuator can be arranged to put air above the piston or below the piston. In this case, air is added above the piston, forcing the piston, stem, and disc downward. When the air pressure is released, the spring moves the piston back to the fully upward position. The piston valve actuator fail position depends on design or spring position. If pressurized to open, the valve will fail closed. If pressurized to closed, the valve will fail open. It can be operated remotely. It is typically used on small valves. Another pneumatically operated actuator used for larger valves is the rack and pinion. When referencing gears, a rack is a straight gear while a pinion is a round gear. In the rack and pinion, two pistons have racks or straight gears in contact with a pinion or a round gear. When air is inserted between the pistons, it forces the pistons outward against the spring pressure. The racks on the piston cause the pinion to turn, which turns the attached valve stem. These are used on short throw valves, 90 degrees to open or shut. They have a position indicator on top of the actuator. When air is inserted between the pistons, racks rotate the pinion, which rotates the valve stem. When air is released, the springs force the pistons inward, racks turn the pinion, and rotate the valve stem closed. The rack and pinion actuator is frequently used in LWO. The failure mode for the rack and pinion actuator is closed. It can be operated remotely. It typically has a local position indicator mounted on top of the actuator. Hydraulic operated actuators use a non-compressible hydraulic fluid, typically oil, to operate valves. Just like the pneumatically operated valves, hydraulics can be set up to operate against a spring so that when the hydraulic pressure is relieved, the spring repositions the valve, or set up so that hydraulic pressure on one side of the piston moves the valve one way and on the other side of the piston moves the valve in the opposite direction. Hydraulics can be used to operate large and very heavy valves. They are often used in power plants operating massive equipment. Hydraulics is rarely used in LWO facilities. The failure mode of an hydraulic actuator depends on the valve design and setup. When using oil as a medium, leaks can cause the oil to aerosolize, making it a potential fire or explosion hazard, which is why it is rarely used in our facilities. Hydraulics can be used to develop large amounts of torque to operate large valves. Pressure-reducing valves are a specially designed valve that automatically reduces downstream fluid pressure to a set pressure, for example 150 psig to 50 psig. This allows for the proper pressure to be applied to each system or component. The desired output pressure of the reducing valve is set by positioning the adjusting screw, which adjusts compression on the interior spring. The adjusting screw forces the adjusting spring to push downward on the controlling diaphragm. The downward force on the controlling diaphragm is opposed by the outlet pressure of the reducing valve acting on the bottom of the diaphragm. Most reducing valves are reverse seated, move upward to close. In a simple reducing valve, there is a sensing hole which allows downstream pressure to be felt on the bottom of a diaphragm. The disc is attached to a valve stem that is attached to a diaphragm. The diaphragm has spring pressure acting on top and downstream pressure is felt on the underside. If downstream pressure is less than spring pressure, the diaphragm will flex downward, forcing the stem downward and moving the disc off the seat, allowing increased flow through the valve. The outlet pressure can be adjusted by compressing the spring to maintain downstream pressure higher or decompressing the spring to maintain downstream pressure lower. The valve will typically find some throttle position that maintains pressure for a particular load. A pressure-reducing valve automatically reduces downstream pressure to set pressure, which is determined by the set screw adjustment. The downstream system helps position the valve, acting on the bottom of the diaphragm. The failure mode of the valve depends on what type of failure occurs, such as a spring break or a diaphragm rupture. Valves used in steam systems are very hot and should be adjusted using the appropriate PPE. Relief valves and safety valves prevent equipment damage by relieving accidental overpressurization of fluid systems. Relief valves are used on non-compressible liquids such as water, oil, etc. A relief valve gradually opens as the inlet pressure increases above the set point pressure, and it only opens as much as necessary to relieve the overpressure condition. This minimizes the amount of liquid lost. System pressure is felt on the underside of the disc. If system pressure overcomes the pressure of the spring acting on the stem and disc, the disc will lift off the seat, allowing flow through the valve and out of the system. When system pressure is below the set point of the relief valve is closed. If system pressure increases above the set point pressure of the relief valve, the valve will open to allow flow and reduce system pressure. The higher the system pressure is above the set point, the more the valve will open. For non-compressible fluids, it generally does not take much relief action to reduce the system pressure. A relief valve will gradually open as the inlet pressure increases over the set point. The valve will open further if the system pressure rises above the set point pressure and at some point be fully open. The mathematical difference between when the valve is fully open and the set point pressure is called accumulation. The purpose of a relief valve is to protect equipment by relieving accidental overpressurization. A relief valve is used for incompressible fluids such as water or oil. Relief valves have accumulation. A relief valve set point is adjusted by adjusting spring compression using adjusting screw and nuts. Safety valves, on the other hand, rapidly pop fully open as soon as its pressure set point is reached. It will remain fully open until the pressure drops below the reset point. The reset pressure is a lower pressure than the set pressure. Safety valves are typically used for compressible fluids such as steam, air, or other gases. Safety valves can often be distinguished by the presence of an external lever at the top of the valve body, which is used for operational checks. Since a safety valve is used on compressible fluids, it takes a larger volume to have an effect on system pressure. When the set point is reached, a safety valve pops fully open. It will remain fully open until some point below the set point pressure is reached. This is so the safety valve will not immediately open again and prevent valve chatter, rapid opening and shutting. The difference between the set pressure and the reseat pressure is called blowdown. It is expressed as a percentage of set point pressure. Just like a relief valve, a safety valve protects equipment by relieving accidental overpressurization. Safety valves are used for compressible fluids such as air or steam. Safety valves have blowdown. The set point is adjusted by adjusting spring compression using an adjusting screw or nuts. A valve positioner controls the valve actuator. A positioner controls the operating air pressure to the diaphragm to fully open, fully close, or some throttle position in between. The positioner may have feedback from system pressure, temperature, or flow instrumentation to provide input so the positioner can adjust the valve position to maintain the desired set points. This video shows an air-to-open actuator, forward acting, where air is supplied below the diaphragm with a normal seated valve. Supplying air will cause the diaphragm to move upward, opening the valve. If air is removed, the spring above the diaphragm will force the diaphragm down to close the valve. The positioner provides pressure to position the valve based on the control signal. As pressure under the diaphragm increases, overcoming spring pressure, the valve stem will begin to rise. If pressure under the diaphragm is reduced, the downward force of the spring lowers the valve stem towards the closed position. Valve positioners are used throughout LWO on pneumatic control valves. They are usually mounted on the side of the diaphragm actuators. The positioner controls the valve actuator by supplying the appropriate air pressure to the diaphragm to position the valve in the desired position. They are beneficial in situations that require throttling. 2S Manual Procedure 5-7 Verification Methodologies discusses how to verify various types of valves. To physically check a valve position, turn the valve handwheel a short distance in the shut direction. If the handwheel turns, the valve is open, return the handwheel to its position. If the valve is shut, the handwheel will not turn. If the valve is tagged out by danger or admin tags, verify by checking the position of the valve on the tagout. Power actuated valves typically have a local indicator that provides valve position indication. For valves with remote indication, such as solenoid actuators, valve position indication is provided using open and closed lights or a meter. When open and closed position lights are used, only the open light will be illuminated when the valve is fully open, and the closed light will be illuminated when the valve is fully closed. Both lights will be illuminated when the valve is in some mid position. Use system indications to check valve positions as a backup to physical verification. Examples of system indication include listening for flow noise, feeling pipes for flow, vibration, or temperature changes.